Hello, my name is Amobi Onijaka, and today I will be doing my presentation on system dynamics and control. In the table of contents, we're going to briefly discuss an introduction to system dynamics and control, the application of system dynamics, modeling of mathematical and mechanical systems, abstract as well as design requirements. Then we're going to shift into the physical setup of the model, system modeling, and then we'll end with the MATLAB code. System dynamics is an approach to comprehend the behavior of a complex system utilizing flows, feedback, loops, functions, and time delays. System dynamics is defined as the mathematical modeling of dynamic systems in order to establish a protocol or a process necessary to design and optimize a complex system. There's two aspects to this course. There's the system dynamics, which deals with the modeling, and then there's a control aspect. And that focuses on operating a dynamic system. In the control system, the controller monitors the system inputs versus desired outputs and makes necessary adjustments. Here we have a block diagram. What happens here is the reference is at some point will be treated like an input into the system, which goes to the controller, and the controller makes whatever adjustments necessary and sends a signal to the system to carry out the input. The system output is now measured by the sensor, and the measured output will be fed back into the controller to make the necessary adjustments. Application of system dynamics control. We're going to discuss flow controls. In modeling mechanical systems, it is important to establish a flow diagram that analyzes all processes. This is a way to visually illustrate what the system is going to look like and the processes that it goes through. The change that occurs within a system have to be timed and measured in order to adjust input to achieve the desired output. So sensors play a major role in the system because it has to measure the changes happening in the system and give us a feedback that allows us to make the necessary adjustments to achieve the desired output for that system. Continuing the application of system dynamics and controls. Modeling the system allows the designer to optimize and make improvement prior to manufacturing. This is a cost-efficient approach to developing a mechanical system. If I were to model a system, I can run simulations, which allows me to see and adjust different criteria of the system prior to the manufacturing process. Even after the manufacturing process, we still need to test the system to make any last-minute adjustments before we roll out the system. Again, this is another example of a block diagram. In this particular case, we're focusing on the transfer function and the input and output functions. Typically, when you model the mathematical equation to govern any motion, you have to now take the Laplace transformation to get into the edge domain. And then from the Laplace transformation, you'll now be able to derive the transfer function for that system. And all the transfer function is just a ratio that compares the output over the input. What are we achieving versus what we put in and what we want to achieve? Modeling mechanical system, modeling cost suspension systems. In this particular project, we're going to focus on a cost suspension system. And it's typically modeled as a physical system, but it also has damping effects, stiffness effects, as well as some mass elements of that system. Here's a picture of an actual car controller system, car suspension system, but it's also translated into a mechanical drawing that allows us to simplify, but yet understand what's actually taking place in this system. We have to also establish a design criteria for the system, what we hope to achieve in the system. This is very important because it gives us a set of guidelines that we have to make sure that our system follows. Design criteria creates the parameters that allow you to design your system effectively to achieve whatever results in desired outputs. In this particular case, what we're looking at in the criteria is to consider how the suspension system would behave when it goes over cracks and rides on uneven pavement. How would it recover from oscillations when it vibrates? how is this going to affect the passengers inside the car, and what necessary changes can be made to address these issues. The road disturbance in this problem will be simulated by a step input. The step could represent the vehicle coming out of a pothole. We want to design a feedback controller so that the output has an overshoot less than 5% and the setting time shorter than 5 seconds. For example, when a vehicle runs onto a 10 centimeter high steep, the vehicle body will oscillate within a range of plus or minus 5 millimeters and return to a smooth ride within 5 seconds. So in other words, as the car goes over the bump, the vehicle is going to oscillate. But we don't want the oscillation to become unstable because it's going to be very uncomfortable for the people inside the car. We want to minimize that oscillation and also bring it back to an equilibrium point in less than 5 seconds. Because what happens if the car continues to vibrate, the oscillation can reach natural frequency, which the car will vibrate out of control and become unstable. Here's another example of the physical setup. We model the body, the mass one as the body of the car. Keep in mind, there's 4 wheels in the car, so this only represents 1/4 of the total mass of the car. And then our mass 2 represents the suspension mass. The system itself, the suspension system itself, has a mass element. Between the mass of the car and the mass of the suspension system, we have some stiffness due to rods and different mechanical elements, and also some friction, which here is modeled as a damper. And between the car suspension and the tire and the road, we also have some stiffness, again, mostly due to the tire stiffness, and another damper that kind of represents the friction between the tire and the road. And setting this up, we kind of begin to now come up with a set of equations that we can use to predict the motion of this car suspension system. During the system modeling, we have to first model the system utilizing sum of force system we've learned in physics class. And then as we continue to model the system, we have to come up with 2 sets of equations that governs the motion of the mass of the car and also the motion of the mass of the suspension. From those 2 equations, we're going to be able to take the Laplace transformation and derive a transfer function for both masses. Once you set up your transfer function, you can now go into MATLAB, input your variables, know your known variables, along with your transfer function, and you're able to produce a step response. This graph here represents a car going into a pothole. As you can see, it does have some vibration, but over time, it starts to even out and become stable again. But this does not necessarily meet the criteria by design because it takes it entirely too long to stabilize. It takes approximately 35 seconds for the system to stabilize, which based on our design criteria, we want to get all this within 5 seconds. So we got a long way to try to achieve that. And there are many ways we can do that. One of the ways is to look at the disturbance based on the magnitude of the force acted against the tires. And the smaller the magnitude, the less of the disturbance will be, which is shown by this second graph. It's still taking us about 35 seconds to get stable, but the oscillation is not as severe as the first graph. So if someone riding in a car, this car would feel a lot more vibration when you go over a bump than the person riding in this car. And in conclusion, the car suspension system can be modeled mathematically. The mathematical model can be used to study the system, create control, design and create a control system for this, and also help us understand how the system interacts with its environment. Going back to the abstract of this project, the purpose of this project is to model a car suspension system and generate values that will help in predicting the system behavior. We're going to have a set of fixed values, like the mass of the car won't change, the mass of the suspension system won't change, but other values we can manipulate to achieve the desired output. Thank you very much.